Okay, bit of a shorter video for the final part of the integral, improper integral section. There will be, well, I'm going to start off with some results that are just useful, that are kind of worth, well, definitely worth remembering if you can. Normally I would do kind of a longer, thorough proof, but it does take a long while. So perhaps one of the teachers next year may go into doing that. But it dips into lots of other bits of maths in order to do the proof. So for now, I'll just tell you the couple of results and just kind of give you the heads up to watch out for them if and when they do occur. Otherwise, the results aren't obvious, I suppose. So we'll get to those later away. So the first one is, when you're doing these kind of integrals, is if you need to work out, I might just put some key results, I suppose. So for any real number, call it k, if you end up with a situation like this, we have to do the limit of e to the k times e to the negative x as x tends to infinity. Then you've got to contend with the fact that, okay, so as x tends to negative infinity, this is going to make the e to the negative x tend towards 0, but then you've got x to the k almost kind of combating against it, I suppose. So it's kind of like, it's almost a bit like which one's going to win in this product. And I suppose hopefully, if you're not considering k tending to infinity, you're considering k as a real number, then hopefully it's not too hard to see that that's the e to the negative x, if you like, is going to win out, if that makes any sense. So e to the x to the k is just going to represent some real number, and it might be absolutely ginormous and positive, but e to the negative x as x tends to infinity, well, the infinity, that sort of vastness of it, even though we're kind of considering a limit, that's going to sort of win out, if you like, which isn't a very official way of proving this result, but it's certainly an intuitive way perhaps to help you remember it, because I did say at the outset of this video, you're going to have to try and remember these unless somebody does do the full proof with you, which is very interesting, but like I say, it just takes quite a long time. Okie doke. So that's the kind of first result, which is important to note. The other one is that for any real number again, and we'll just call it k once more, and it's a kind of similar idea, x to the k times by ln of x this time. Okay, so, and this time it's when x tends to 0. From the positive side, to be clear, I was tempted, I thought this might have come up in one of the previous videos, but it didn't in the end. If you've not come across it before, all I mean by that is when you consider limits, oops, and when, oops, that's, yeah, just about doesn't touch, I wouldn't lose a mark there, it just about doesn't touch. So if this is ln of x, say, okay, this graph, then when you're dealing with asymptotes, which this vertical axis is, you know, it's acting as an asymptote, then you're considering a limit, you need to then take care of which side of the limit you are approaching from. That's the correct terminology there. So obviously we know that you can't have ln of 0, x cannot take 0 in this function, it's undefined, and it also can't take any negative values. So when we're talking about the asymptote, we can't talk about it being 0, we need to talk about it approaching 0, and with things like infinity, well, if it's positive infinity, it's kind of obvious, you can only approach from the lower positive end and going up to positive infinity. For negative infinity, you can only possibly be approaching by going downwards towards negative infinity, because you can't get lower than it. But if you're dealing with something like this, where you're talking about obviously the point of discontinuity where x is 0, then you kind of have to just be clear that you're talking about as x approaches 0 from this side. You can't approach it from this side, so it has to be from when x is going from the positive values and approaching 0 from that end. Okay, because you kind of want to, I mean, we know that the limit would be 0 because we've dealt with this function quite a lot, but it's just the fact that you'd be inching your way down here slowly and slowly and slowly, well, forever, because it's a limit. But the important point that I've probably made a little bit too much now is that we're coming from the positive side in this case, and that the only reason why I'm sort of mentioning that is that sometimes people aren't quite aware of the symbol, the notation, which is just simply 0 plus, or 0 positive, I should probably say. Okay, and so I've left a gap because it's what is the limit then? So we've got x to the k times by ln of x. Well, I feel like if that one was intuitive, you can probably imply the same sort of intuition to this one, which is that the infinite nature of the limit, this is more of an infinitesimal one because it's approaching 0, is kind of going to win out here. So if that bit itself tends to 0 and this bit doesn't, the kind of times in by 0 bit, it turns out, again, it's not very rigorous this, but that's the bit that wins out, so it will actually end up equaling 0. Okay, so you might come across that in a question. I mean, the one that they've got, for example, in the Caboodle textbook is as follows, and it's just a case of trying to remember it and spot it really if and when it does come up. So if you had that, let's just take a quick look at this example. It's not the longest one in the world. Okay, let's get started properly now. So we're going to have to introduce a limit. Hopefully you can see why. It's the ln of 0 that would cause the issues there. And this, it's not necessarily going to tell you this in the exam that you need to set this up properly. You need to spot the improper integrals to gain the credit, really, to show that you're aware and that you address and look at situations before you dive in and put pen to paper. It's kind of obvious at the moment because we're within the topic, but that's going to be one of the skills that you're going to have to practice. Okay, so we set up the limit and introduce a variable t. We need to actually compute the limit, which actually you may not have come across yet how to integrate ln of x. I'm not sure if you've necessarily done that. Let me see if you've done that. Probably, maybe not, but that can be one to look up actually. So if you want to pause now, then definitely look it up. But I'll give you a clue because there's a bit of a special technique to doing that one. Integral of 2 is obviously not going to be an issue. I can put that in straight away. 2x. Yeah, if you want to challenge yourself, let's put the minus in as well. Just as an aside, the integral of 2x. Here's another aside. Sorry, what am I talking about? Integral of ln of x with respect to x. Once again, you're just eating through the single side of pure mathematics at the same time, and that, as I keep on saying, is the benefit of doing further maths. You may not know where to start. I mean, you could try that idea of inspection and try anti-differentiation essentially. So try some things and differentiate it to see if you get ln of x. That might work. It's a tricky one though, because you sort of might be stabbing in the dark a little bit there. But then what do you do if you've got nowhere else to go? Now you can run through some of the techniques that you know. Try substitution. Maybe you'd have to write, I mean, you can't just substitute x for u, that's going to get you nowhere. So you might have to force, I don't know, write it in a different situation, a different format perhaps, and see if you can do a substitution. Or, and I've just paused to kind of give you enough time to think of options and maybe pause the video. I'm going to give the big clue away now. I mean, you can pause it after this if you want to really, just to give it a go, because this is quite a common classic one in year 13 single maths. And I don't want to blow the result for you, if you see what I mean. Integration by parts. Okay, that's the clue. There's a secondary clue that's following up here as well, because you may well, quite rightly, be thinking, but there is no product here. It's certainly not ln times by x, because ln's the function. So you've got no product going on. All I'm going to say is create a product. Force there to be a product there. You've already got ln of x, so introduce something else basically, and without changing the question. There you go. There's the second hint. And see if you can use integration by parts to get a result. If you can, then obviously you can differentiate it and check that it's correct. Okay. Okay, so spoiler alert, the result is coming up now. Pause the video, come back to it another day if you want to save yourself time, because you only ever get one chance now before I blow it and give you the results. But after this, you may see it. You might see it in loads of different questions, I guess. Okay, here's the results. Obviously, we're doing ln of x, so it's x multiplied by ln of x, subtract x. Not an obvious result, I think it's fair to say. Okay, and quite interesting to see if you can differentiate that. You should be able to do the product rule there. So differentiate one, keep the other, keep the first one, differentiate the other, add those two results together, and then obviously differentiate that as well. Okay, that is really nice the way it cancels out. It's good, always good to check and practice just to justify and help with your own memory, I suppose. Especially with it being a sort of quite a classic result. Anyway, we've performed the integration, so now we can actually get to substituting those limits in. Okay, and this is what we get. We get 2 times 1 minus 1 ln of 1. Shall I write it in? I'll write it in for now. 1 ln of 1 plus 1 if I forget about this set of brackets, and then we get minus, I need to put t in now, 2t minus t ln of t, and I've run out of room, which is annoying, plus a t again if I kind of expand the negative, the subtraction into that bracket. So the limit of all of that, if we just tidy that up somewhat, we've got the limit of 2 plus 1 is 3 minus 3 t's altogether, because we've got 2t plus 1t, and then that's all being subtracted. Ln of 1 is 0, so we can not worry about that, and then we've got plus a t ln of t. That's the big final result. And oops, I've used an equivalent symbol there. So limit of 3 is just going to be 3. Limit of 3t, of course, is going to be 0 when t tends towards 0. And then this bit, well, fortunately, that's of the form x to the k ln of x, which is brilliant because that sorts us right out, and we know that that's going to tend towards 0. So actually the answer would be 3, and we can just say, since 3t tends towards 0 as t tends towards 0, and t ln of t tends towards 0 as t tends towards 0. Perfect. So the answer is 3. So there's a kind of scenario where you might use one of these results, okay, which is kind of hopefully not too hard, but it's quite a nice little one there. Okay. Final section that we're going to consider in this topic is just a small technique which is worth mentioning. It's not very fair to not mention it, and it's just if you had something like, let's just come up with something, for example, 5x cubed minus 7x squared, and I'm going to make it a fraction, divided by, is this the kind of thing I'm after? Let's make another value here, something like 2x plus 6x to the 5. Let's just go with that for the time being, and let's consider if what happens if we are trying to consider the limit as x tends towards 0. Okay, so we're going to go for the limit as x tends towards 0 of all of this shebang. Okay, and what's interesting about this is that obviously when you look at doing it and if you just put 0 in, which for a lot of limits that might well work, kind of almost just substitute 0 in and hope for the best. That's kind of obviously not fully considering the notion of a limit, but it often will work for you. But if you do that in here, you're going to get 0 divided by 0, which doesn't really help very much. So what we can do is say, well, this is exactly equal to the following limit. And all I'm going to do is go back to primary school, which might surprise you at this level, because lots of the work from primary school, still holds throughout mathematics, and all I'm going to try and do is use the property of equivalent fractions, because we know that if we divide the numerator and denominator by the same value, the fraction will be equivalent. So it's just what I choose to divide by that's the clever step. And if you go for you'll see why shortly, if you go for the highest power of the variable, in other words, if I divide through by x to the power 5, in this case, throughout the whole numerator and whole denominator, I can't just pick and choose bits of the numerator because there are separate terms. Okay, remember, this is a one big fraction, so I need to do it to all of the numerator, all of the denominator. Let's just see where that gets us. So I'll get 5. Well, if I divide 5x cubed by x to the power 5, I'm going to get 5 over x squared. And I don't know why, but for me, for some reason, I prefer to write it out as a fraction rather than 5x to the negative 2. You might not sort of join me on that. You might prefer to write it as 5x to the negative 2, but I like to see it as this, and maybe you'll see why shortly. Similar kind of thing, if we do divide 7x squared by x to the power 5, you're going to get 7 over x cubed. Don't need these brackets really and these colours, it's just to make it really obvious. The 2x is going to become 2 over x to the 4. Hopefully I've not made any silly mistakes here. And as was always going to happen, I'm going to get left with whatever the coefficient is here, which is just a 6. And why that's useful is because we know, so 0 divided by 0, we know that causes issues, okay, it's indeterminate. Whereas this is going to equal, well, that's going to tend towards 0. Oh no, sorry. I think what I meant, well, it's going to be divergent there, isn't it? Excuse me just for a moment. What I'm going to do, it doesn't really change too much about what we've said. I think what I was getting at here is I wanted to do infinity. You might see why now. I think that's what I had in mind when I made this one up. If we just change the limit to infinity, so excuse me there for changing that. We're still in this funny situation where you would have got some, I guess, infinity divided by infinity. You've got this weird thing going on. I mean, you've kind of got an infinite amount plus an infinite amount. You've got, I mean, is that a big infinity minus a small infinity? You can really go down a rabbit hole here in that situation. But having converted it, I can continue with what I was going to try and do there. We can say that the limit of 5 over x squared as x tends to infinity, well, we know that that's 0. And we know that the limit of 7 over x cubed is 0, and this will also be 0. So actually, the limit, and I can put equals now because I'm referring to the limit, I'm working it out as a limit, is 0 divided by 0, 0 plus 0 divided by 0 plus 6. The 6 obviously won't be affected by whatever happens to x, which is, of course, 0 over 6, which is 0. Now that's quite nice because that's just a simple, quick move that's got us into a format where it's just there's no argument now. Okay, and these two are obviously equivalent, so it's a really nice little move to convert from there to there. So that's the sort of technique that I suppose I'm getting at. And it won't always work out as 0. It works for other things. So let's just say, for example, I had the limit as x tends to infinity of I don't know, x squared plus 7x divided by let's go for 5x squared minus 8. Okay, and we see what happens in this case. Well, if you pop infinity in at the moment, again, you've got this sort of weird issue where you've got infinity kind of plus infinity. You can't really substitute x in as infinity, but that's the kind of idea that you're working towards on the numerator. And then you've got this sort of big infinity minus 8, which is still infinite. You still got a funny situation going on there, and it's, I mean, good luck to you to try and figure out what that is when you put x as infinity. So a similar technique to what we've just looked at. Highest power is x squared, so if we divide through by x squared on the numerator and denominator and see what that gives us, then hopefully we can see we get a 1 there, which is nice, plus a 7 over x. I really don't need these brackets in, I'm not sure why I'm putting them in. Here we get a 5, and here we get an 8 over x squared. Okay, which I'm hoping it's therefore quite clear that that limit equals 1 plus. Quite often you see it, the reason why I'm kind of emphasising this here and here is that quite often people write the limit in here and that they've lost sense of the precision, really. The limit of this is exactly the same as the limit of that, but the limit of that absolutely equals this, because you've acknowledged the idea of putting x in as it tends towards infinity, and you've considered the limit at that stage. So x tending towards infinity gets you 0 when you consider 7 over x. 5 is just 5 minus 0, and so actually you can see that this one turns out to be a fifth. Okay. Not immediately apparent, I think, from the original questions there, so that's just kind of something to watch out for, I suppose. And I think I've just got one question that's based on that, really. Okay, so piece of paper. Let's go over to here. Okay, so the problem is, just make sure this is on the screen properly. There you go. Okay, it's the integral of 2 up to infinity of 1 over x minus 1 take 2 over 2x minus 1 dx. So, just give you a moment to have a go at that, and I'll come back to you in just a moment. Okay, let's just get going on this one then. So the integral of 2 up to infinity of all of this. What we need to do is, obviously, when we're not when we've not got our heads into this topic, is just kind of be ready and aware to assess the situation. So hopefully it's not as hard as some of the previous topics, because the infinity and the limit should give away that it's an improper integral. And when you try, you might sort of, it'll dawn on you that you can get into a mess unless you consider the limits. So if we actually do that, as we normally do, I could split this up as 2 separate integrals if I wished. Don't think there's any need to for now, as long as I'm aware it's the limit of all of this. Okay, and I could put another set of brackets in, but I know as long as you're clear as to what's going on here, then that's not a problem. Okay, usual step, we need to actually perform the integration. It's not a hard one, because notice that it's of the form f dashed of x over f of x. So if you differentiate the denominator, you get the numerator exactly the same in there. So it's actually in the perfect form to be ln of the denominator, which is handy. Don't even need to do any adjustments. Put the limits in. We can now tidy that line up slightly by putting in the, before we do that we need to actually put the values in, but I might tidy up at the same time, actually, because we know that if we've got ln of something minus ln of something else, we can write it as 1 natural logarithm of this divided by that. So that's going to be ln of, when I plug in the t in place of x, ln of t minus 1 over 2t minus 1, subtract ln of, that's going to be ln of 1 when I plug in 2, and that's going to be ln of 3, so it's going to be ln of, subtract ln of a third, but if we're going to be fancy about this, ln of a third is 3 to ln of 3 to the negative 1, bring the power down to make that into a plus, and I can just tidy it up as ln of 3. Feel free to rewind that, or just give it a go for yourself. You may well have just kept up with that, otherwise just do it in a couple of stages and hopefully you can see where I got ln of 3 from. Not that it has to be written as ln of 3, it could be minus ln of a third. Okay, here's the step then where what we talked about kicks in. This is kind of what we were building towards, because you try and put in infinity into this natural logarithm within the limit, and you find yourself stuck. So you potentially could make no more progress at this stage unless you employ the nice little tactic that we just referred to earlier, and divide through by the highest power of the variable, in this case t to the power 1. If we do that, then the fraction within the ln becomes 1 minus 1 over t over 2 minus 1 over t. Okay, and I just think it's a really nice little technique. Don't need to worry about the ln of 3. A really nice little technique to be able to deal with limits, particularly these limits regarding infinity, because you can see that that's going to tend towards 0, so is that. So it's going to end up as equal to ln of a half plus ln of 3. Okay, and we can probably just justify that and back it up slightly and say, since let's see if we can do it all in one go. Since ln of 1 minus 1 over t divided by 2 minus 1 over t tends towards a half, as t tends towards infinity. Okay, and then we can tidy this up a little bit, can we, I suppose, because we could say, well, we could multiply the two things together and just get ln of 3 over 2, I suppose. That's probably easier than putting it as 2 to the negative 1. So use the fact that if they're adding two natural logarithms, we can multiply the arguments together, and there we go, ln of 3 over 2. And that's how you might just use that little technique that we talked about there. Okay, I think that will probably conclude the work on improper integrals.